Good morning. Good morning. I feel like saying hallelujah. So thank you, Chad. I'm truly delighted and thrilled to be part of this celebration and this rather remarkable journey of the last 2 decades with many exciting destinations yet to come. So first, my hearty congratulations and compliments to you, Chad, and the whole IIN team for all the amazing achievements and accomplishments you'll see in the rest of the day today. I'm also going to give a shout out to some of my 190 freshman students who I see in the audience. So nanotech actually touches every aspect of Northwestern, including freshmen who get use of these fantastic nanotech toys. So again, I'm glad that you could be here. So the theme of nanotechnology is intrinsically interdisciplinary and collaborative. So I'm very thrilled to join on the podium with Teri, Odom, and many other inspiring colleagues within IIN. So we'll play a tag team first. So I will start the introduction of Nano, and then Teri will take over, and then I'll come back and bring you home. So this morning session, as Chad mentioned, is really to set the stage and emphasize some of the core principles and opportunities in this very exciting field of interdisciplinary nanotechnology. So I'll start with the first slide. I call it, I start with this slide quite often, and it doesn't get old. We call it the nano zone. So this is the sort of a sandbox of nanotechnology. Oops. Okay. So on one end of the spectrum, you have the single nanometers. It takes about 1 billion nanometers to make 1 meter, so that gives you a sense of how small that is. And at this end of the spectrum, this image reflects almost like a molecular abacus. So each of the white dot that you, the C60 molecule is a single molecule. So on one end of this nanospectrum, you have abacus, you have 660 molecules and molecular structure on this end. On the other end of this nano zone, you see is the dreaded SARS-CoV-2 virus that really decimated the world in the last few years. And this is of the order of 90 nanometer. And in between, you have physical, biological, and hybrid nanostructures. So this is really the true playground of nanozone or nanotechnology. But a part of the nanotechnology motivation is not just about the size and being very, very small, but it's also about size and shape-dependent phenomena that really change the character of the material at that length scale. So for example, here it's not just about miniaturization, which has been used, the nano prefix in so many technologies. But if you see this very carefully, this is the butterfly wing, and it gives you different colors depending on the different direction of the light. And so these are actually natural photonic bandgap material where the light squeezes and changes the color or the frequency. So nanotechnology is not just about miniaturization, but it is also size and shape-dependent phenomena, which are very different than their bulk counterpart. I also want to emphasize that often we do nanoscience, which is we do creativity without much constraint in terms of cost or other considerations. And one of the best examples I often give is that of transistor. So transistor effect was discovered in 1947, later on led to Nobel Prize. But it took several decades of investment, R&D, of engineering to go from science to engineering to technology. So it takes several decades for science to translate into technology through the bridge of engineering, we often call it. However, nanotechnology has been remarkable in that sense. I think the sort of our time to market is now shrinking in this modern world. And so this particular graph on the top, I've drawn from a National Nanotechnology Coordination Office, which projects how the technology evolves. And this is a summary which says that Nano 1, the first introduction of nanoscale products have been nanoparticle, nano objects, as well as instruments and techniques to observe nano. And the second evolution of nanotechnology is Nano 2, where we are looking at nanoscale systems, where the nano is an integral component. And as we'll see rest of the day today, there will be Nano 3 opportunities that you will see. In the meanwhile, a lot of consumer products and other developments have occurred over the last couple of decades. And in our day-to-day lives, you will see a lot of products which have nano-enabled capabilities, whether it's sports and other consumer products. Obviously, initially, nanoscale is very analogous to biological length scale. As a result, the initial development have been in biological structures, pharma, diagnostics. And this is where I think the nano converged very well during the COVID pandemic. So if you remember early pandemic in March 2020, tremendous shortage of the personal protection equipment. So initially, the nanotech community really rose to the occasion and addressed some of the initial PPP needs that we needed. So a lot of the personal protections, you can imagine the SARS-CoV-2 is the nanoscale object, so you need materials and structures to withstand the invasive SARS-CoV-2. And here you see a number of examples of PPP products which are enabled through nanotechnology. On the other end of the spectrum, as the pandemic moved forward, you see the lateral flow assay. So this involves nanotechnology of antibodies and nanoparticle, which is now ubiquitous, the testing. And there'll be new generation tests that'll be coming up next year. PCR, or the genomic testing to look at the variant, came along very quickly. And now the PCR has greatly advanced and is accelerated in terms of timeline. And truly the culmination in some way of nanotech and COVID convergence is the mRNA vaccine. So you have an RNA inside a lipid nanoparticle, and that generates the antigens for which our immune response gets developed. And this is another example of nano and COVID. So with that, let me pass on the baton to Teri Odom, where she will go over the historical development of nano and Northwestern Nano, and I'll come back and tell you about the opportunities ahead.
Thanks, Vinayak. This is the, Chad has asked us to do this very interesting experiment where he said, okay, independent faculty members, you come together, put together a 25-minute talk, and see how it goes. So this is our version of being creative along these lines. Vinayak has told you about the nanoscale science and technology now, and we're here to celebrate 20 years of nanoscience at Northwestern. But there is some precedent to where we were able to intersect it at just the right time. And so I want to tell you a little bit about that before some highlights to get us where we are today. This is the timeline all the way back from 400 AD to the present. And one of the quintessential examples of the beauty and taking advantage of our artistry of nanoscience is this Lycurgus cup. So the idea is if you have the cup sitting here, it's going to look green to you because it's reflected light. If you put a light bulb inside the cup, the transmitted light is going to have you visualize it as red. So that's pretty neat. It exhibits two different colors depending upon the light and how it interacts with your eyes. The next example is more of a scientific example. This is Michael Faraday's lab notebook. It's very well preserved. This is finely divided gold on these glass sides. So there's a big gap in dates in terms of trying to understand what is the art in these beautiful colors, and then how can we understand what contributes to that. But then it was in 1959, many of you may be familiar with this call to action by Richard Feynman, where there was an invitation to enter a new field of science from this very famous talk that he gave, There's Plenty of Room, at the bottom. And I want to read this to you partly because he was looking forward in a lot of ways, but then we've way surpassed it, which is really neat. So people tell me about miniaturization and how far it has progressed today. They tell me about electric motors that are the size of the nail on your small finger, and there is a device on the market, they tell me, by which you can write the Lord's Prayer on the head of a pen. But that's nothing. That's the most primitive halting step in the direction I intend to discuss. It is a staggeringly small world that is below, and in the year 2000, when they look back at this age, they will wonder why it was not until the year 1960 that anybody began seriously to move in this direction. Why cannot we write the entire 24 volumes of the Encyclopedia Britannica on the head of a pen? Okay. So this was the call to action and a challenge in 1959. So this was some of the first ways to think about small systems. But then the Nobel Prize was given in 1986 for two tools that actually allowed us to see things at the nanoscale. The first tool was the transmission electron microscope. And, whoops, I'm sorry. Where this is where we were finally able to understand what is resulting in these colors, and that is from some silver gold particles. So finally we can understand what is happening at the nanoscale there. And then it was also given for another characterization tool or manipulation tool called the scanning tunneling microscope. So taking advantage of electrons to be able to manipulate atoms and also to understand nanoscale materials. And this is really important, which we'll get to later on, is the importance of tool development in order to be able to resolve nanoscale structures. Then the Nobel Prize was given for a nanoscale material, C60, about a decade later. So this is all very exciting, fundamental work. But in order to move the work forward, we have to have someone that says we're going to invest in that. And so this is why the United States was leading this charge over 20 years ago by the launch of the National Nanotechnology Initiative. Where he said, soon researchers will bring us devices that can translate foreign languages as fast as you can talk, materials 10 times stronger than steel at a fraction of the weight, and this is unbelievable to me, molecular computers the size of a teardrop with the power of today's fastest supercomputers. So even back 20 years ago, we were thinking about information processing, superior materials, molecular electronics, atomic electronics. So this was 20 years ago. Right? And we've done a lot since then. But the point here is you have to have investment to make some of those things happen. Okay, then in 2007, there was another Nobel Prize for nanoscale ideas, and this is for giant magneto resistance, so observing these types of properties in other types of materials. And then finally, in 2008, a new prize was awarded, which is called the Kavli Prize in nanoscience and a couple of other fields. And it was the first one dedicated specifically to emerging areas, which I think is really important to recognize emerging areas in the beginning so that more people can participate when it's most exciting. And this was awarded for two other types of nanoscale materials, for colloidal semiconducting quantum dots, as well as for carbon nanotubes. And these are also a scanning tunneling microscope image, as well as a transmission electron microscope image. So you see how it all comes back with the tools and the materials and the resolution. Okay, and then finally, another award was made in 2016 in nanoscience to one of our own, Sir Fraser Stoddart, where he was awarded jointly this prize with some other friends and colleagues of his for the design and synthesis of molecular machines. So this is the history from sort of just the beginnings of it all into where we are today. And I just wanted to make a comment related to Chad's picture with Mark in front of the outhouse. I was a graduate student at Harvard, and Chad was one of the speakers, and he was talking to us at lunch, and he's telling me about this nano building. It's like the first one in the world. I was like, what is a nano building? And why does anyone care about it? But he was ahead of his time. Buildings actually matter. Buildings matter, period. And if we don't have that type of infrastructure and support, then we can't go forward in the way that we might. Okay. What has differentiated and distinguished Northwestern from many other places, and we've been far ahead in this, is the integration of theory and experiment. Right now it's common, but we were some of the first to really take advantage of that. And so I wanted to go back a little bit for over the last couple of 20 years or more related to the history of Northwestern, because all day today you will hear about what's happening now. Mark Ratner published this seminal work related to molecular electronics, and places. In 1974, it's a while ago, and is the idea that can a molecule function in some type of circuit? But it took a while for that idea for an electron to go from here to the molecule back to the electrode for it to be realized for molecular electronics. But it did happen. He predicted it, and then it was finally realized. Similarly, Rick Van Dyne was able to see spectroscopic signatures of this molecule pyridine on what they called, or what he called, roughened silver electrodes. So this was very surprising. From this vibrational, from this molecule, this vibrational pattern emerged. But why can you see it at very low concentrations on this roughened electrode? And then, of course, our resident expert, George Schatz, said, "Oh, this is what's happening, and this is why you were able to see these types of signals." So it's this an example of this tight integration of theory and experiment, which has really set us on our way today. Similarly, we'll hear a lot about DNA. But some of the beginnings of this was from chemistry, and Bob Letzinger, is the ability to, one by one, add nucleotides in a very descriptive way. And usually that was really difficult. The cleanup was really, really hard. But this was one of these seminal papers related to that. And then Chad worked closely with Bob, not just with companies, but also taking it into completely new areas. So he introduced this idea of these spherical nucleic acids and this 3D presentation that has these constructs show entirely new properties for cancer vaccines, intracellular diagnostics, and even to be able to build new types of atomic crystals that might not have been anticipated. And then, of course, because we're so good at theory and experiment, he worked with Monica to say, okay, what happens if we reduce the density of these DNA ligands, and can we get them to come together and control the way that these effective electrons move in this type of system? So it's a nice tight contribution from both. And then we've also been very good at creating new types of superstructures. I think we'll hear about this next from Sam Stoop and Guillermo. But these were just one of the first ideas. You have these peptide amphiphiles, and by controlling some of the conditions around them, you can assemble them into these long fibers. And so these are transmission electron micrographs of what these might look like. And I should mention that it's not simple to do this on soft materials. And then also, in terms of other one-dimensional structures, Mark Hersom and his group have found really interesting ways to take carbon nanotubes and to be able to separate them based on their electronic properties. And so normally you're ending up with a mix of materials at the very beginning of synthesis, but now different populations can be obtained. In terms of nanomanufacturing, dip-pen nanolithography was one of the first ones from Northwestern, where the idea is you have an atomic force microscope tip, and taking advantage of the natural meniscus that happens in ambient conditions, Chad and his team could write molecular lines on gold films. And then after an expansion of many different iterations of converting these tips into a parallel form and turning them based into polymer materials, they could then they could print down different concentrations of metal salts and convert them to a wide range of different materials for applications that you'll hear about. And in our own lab, we've developed top-down techniques by combining aspects and soft lithography to be able to make a couple of different types of structures in parallel and over large areas, whether they're whole arrays or whether we're making nanoparticle arrays that form the basis for some nanoscale lasers. And then finally, in terms of energy and the environment, McCurry, Kanatzidis, and Bob Chang developed these lead-free perovskite materials that can be solution cast, and these solid state sorry, this is the solar cells without the lead are environmentally compatible and very energy efficient. And then finally, from Vinayak Dravid's group, the ability to make these nanoscale sponges, which are nanocomposites, but to be able to remediate all sorts of contaminants is a big materials advance. And these types of areas related to energy environment are key to what is happening today. And then finally, again, related to nanoscale characterization, which Vinayak is nobly directed over the last at least a decade, maybe 2 decades, I'm not sure. And again, this is harking back to all of his acronyms, right? I just had to close the loop there. But then these types of electron microscopy and cryo-EM, and then these are the types of structures that can be resolved. But part of what I want to emphasize here is that we have to have infrastructure and development for these tools. So you have these huge tools that are very, very expensive, but the payoff is worth it because you can finally resolve these nanometer scale structures. Okay, I wanted to transition to Vinayak for him to close out this session on what's happening next in Nano.
Thank you. So as I try to wrap up, I just want to emphasize some of the core properties and attributes of Nano that really makes it very special. And some of them, I'm not going to go through all of the examples, but some of them to emphasize. For example, Nano intrinsically has a very high surface area. So as a result, catalysis, surface reactions are greatly accelerated. And this is an area that's very germane to renewable energy. If a renewable energy transition has to succeed, we have to find affordable and scalable way to catalyze different materials, sequester CO2 and others. So that's really an intrinsic property, an intrinsic character of the Nano is the very high surface area. Secondly, when you approach that scale, defects disappear. They go to the surface, and you are really actually approaching the theoretical strength of material, very critical as we explore space, and very lightweight material, very high strength weight material, we call this very low energy density. We already talked about how the biological length scale is perfectly aligned with nano, proteins, and DNA. So this is an area we'll continue to grow at rapid pace, particularly in the personalized medicine. Surfaces are an intrinsic part of Nano, so to be able to create molecular scale tailoring so that you don't have to use as much water, reduce waste, that's going to be an intrinsic part of Nano moving forward. And because of the length scale, the electrons and photons don't have a lot of distance to travel before they have to scatter. So as a result, there's an increased efficiency, in, for example, in photovoltaics and other technologies. So what you'll see moving forward, and in some ways today, the microcosm, as you will see, of Nano gazing into the crystal ball of the future, is how Nano is converging with other fields. Clearly, nanomaterials and biology are the intrinsic partners, and they will grow together. Light is the fastest object there is, so to be able to combine Nano with light, there's huge opportunities in nanophotonics, and Teri is one of the consummate practitioners of this field. Nano in energy and electronics is a huge opportunity. Again, for renewable to succeed, we have to have the ability to store energy affordably. And Nano is going to be very big in electrochemical and other ways of storage. Electronics, we've already talked about, Teri, that its inception started here almost 50 years ago in Ratner's lab. On the other hand, you might have seen or heard, obviously, quantum information system emerging. So Nano is a perfect pillar, a perfect anchor for quantum to move forward. A lot of the infrastructure of Nano can be now launched for quantum. We're in the Midwest, and you'll learn a lot about environment, water issues, and how Nano can have tremendous impact. And so we have a lot of opportunities in the Midwest. We call it the breadbasket for the country. In agriculture, environment, we're the home of the Great Lakes. So there are a lot of opportunities for Nano in all of these areas. And last but not the least, some of our students will think of how to integrate Nano with something else. We call it NanoX. And some of our 190 students might advance this field in a direction that we just don't know. So as I end, I just want to give you a sense, a perspective, how technologies evolve over a period of time. And this is a very nice graph to really see how a technology gets incepted, followed by growth and stability and maturity. So it started, as you can imagine, in textile at early stage, and then the rapid growth that led to colonization, among other things. If you look at even the computer or IT, the seeds of the IT actually was sown in the 1940s with the initial part of the computer, and then we had this tremendous growth with microelectronics that continues to grow. So we like to think that nanotech, it has this nascent period with rapid growth, and as we go from industrial revolution to information revolution, we'd like to think that the nanotech, the better days are still ahead of us. So with that, I want to just stop here and just try to challenge you to think small, to imagine big, which is the promise of nanotechnology. So with that, thank you for your attention. We'll be happy to take questions.
Okay, so the floor is open for questions. If you have one, please stand and use the microphone so we can hear you.
As I said, one at a time, okay?
I have a comment. You mentioned giant magnetoresistance, but the first measurements of the effect was in Northwestern by John Catterson and Hilliard, and they are mentioned in the Nobel Prize. But they didn't explain it. That's why they're not in the Nobel Prize. I just wanted to mention that.
Good morning. Thank you. What you're doing is hard to explain to the layman. So you get things that most of the society doesn't get, which is why PR is so important. How do you evolve that so that the society at large can get the impact and the imagination it takes to grow this kind of a science discipline?
Maybe I'll take a shot at it, and Chad and Teri can add also. So one of the key things that we do here is information dissemination at various levels. So this event like this is one such forum under which we open it to everybody. So a lot of folks from Evanston and elsewhere come here. As a part of our ION centers and other centers, we have outreach program. We have webinars, seminars. So we have museum displays. So we work with the local Museum of Science and Industry as well as Natural History and even Art Institute, for instance. So we have different ways to disseminate information, and you're absolutely right that nowadays the modern science and technology is complex, CRISPR, nano, and so to be able to articulate how that impact, and all of us enjoy the fact that we have taxpayers paying for our research, so we want that societal contribution back. And so we do a lot of outreach at the various level, from local level to regional level, to disseminate the information. And we'll be happy to share with you specific examples.
Yeah, I think that's right. I mean, the bottom line is what's still missing are good books that you can go to that address what the opportunities are here, what's exciting from a layperson's perspective. We're actually working on that. We're putting together a series of different books that are aimed at addressing that. But I think it's pretty common in the launch of a new field where there's a lot of excitement and the scientists get really deep into it, and then you start breaking down some of these barriers to the lay public. But it's really critical because policy and decisions like those that the Clinton administration made to go big in this particular area have a huge impact. And it's on the scientists to not only do the great work, but to communicate properly to those that make financial decisions and policy decisions to step up and do the right thing. Other questions?
Following up on that question, what role do you think the media plays in introducing nanotech to the general public?
You want to take it, Teri?
Okay. Yeah, that's thank you for the follow-up question. It was partly in response to this gentleman's first question. It's not just the outreach and the education, but it's a multi-pronged approach to for education. And the media has a special role in this because they can take it in a good way or they can take it in a bad way. But I'm sort of agnostic about that because it's good or bad. You know, Nano is in the news, and the scientists can always provide their perspective about that. But we are living in hard times right now in terms of science, and so I don't want to comment too much on that related to how the public generally considers science. But I think it is our responsibility to make nanoscience in particular just a new branch of science and engineering. You take chemistry in high school, you take physics, and in elementary school, all the way up. Nano needs to start at the more fundamental levels, so that students can start integrating disciplines. I mean, it's had 20 years to germinate and to settle. I think it's starting to come into its own.
So let me add very quickly. For example, we have a program called nanojournalism, where we want journalism students, communication students to immerse in our facilities or research so they can watch the creativity process and report it in a way that they see fit. And for us scientists and engineers, we learned the storytelling ideas from the journalism and communication students. So there are many avenues by which we disseminate the information.
Okay, we have time for one more question.
From our students, maybe?
Last chance.
There's going to be a quiz at the end, so just remember that.
Okay, well, let's thank Teri and Vinayak for a great presentation.